explanation, but I'd like to clarify the meaning of this slide. So at the end of last class, I checked the source of these slides, and then I'd like to clarify it. So when you consider this like theorem, this is a theorem. This is about relationship between positive recurrence and existence of unique station distribution. Okay, as I said before, they have like if and only if relationship. Okay, but the thing is, we assume that this discrete time Markov chain is irreducible. Under this assumption, this is okay. Okay. So please clarify, and if you have any question, please ask me. Okay. So under this assumption, this chain is positive recurrent is equivalent to chain has the unique station distribution. So under this assumption, irreducibility. Okay. Otherwise, we don't know. Sometimes it is okay, sometimes it is not. Okay. So when you think about, when you try to use theorem, proposition, or some concept regarding this discrete time Markov chain, always you need to check the assumption or some condition to use this. Okay, first, and then you can use it. Check whether this chain is satisfied with the condition or assumption or not, and then if yes, then you can apply this result to get to evaluate something. Okay. And then we are working on limit distributions, finding limit distribution. Actually, what if we consider this discrete time Markov chain is not irreducible? That is, this DTMC is reducible. Okay, or sometimes we can consider discrete time Markov chain includes transient state. Then is there any chance to get limiting distribution? That's the main question of this problem. And then actually, when you consider discrete time Markov chain in practice, okay, you can hardly find irreducible chain. Okay, it means often you face to the discrete time Markov chain which is reducible. Okay, but still you have a chance to calculate limiting distribution. And the first step of this finding limiting distribution is decompose states. Okay, so decompose states. So as we discussed last class, the state space can be partitioned into subsets T and C sub K's. Okay, T is actually the set of all the transient state, and C sub K is set of recurrent state, but in the same set C sub K, these states can be communicated with each other. But for two states in the different C sub K, they cannot communicate. Okay, we call this a closed set C sub K. And then when we consider union of all the set T and C sub K's, then that might be the same as set of state space S. Okay, and we considered example, this one. In this case, T includes state 3, 4, and 5, and C sub 1 includes state 1 and 2, and C sub 2 state 6 and 7. Okay, then you can partition as decompose these states. Okay, and then second step is you can use these two formulas in these two slides. Okay, so you need to check. Okay, in the matrix, I mean limit n goes to infinite, we want to find this one, right? This is actually matrix. If size of the matrix P is n by n, then size of this matrix also n by n, right? Okay. Actually, one element in the ith row and jth column might be the same as probability that xn equals j, x0 equals I, and then limit n goes to infinite. Okay, meaning of this element in the ith row and jth column of this matrix limit. Okay, limiting matrix with limit of n. Then this one is actually has the meaning of this conditional probability. Okay, so you can check whether where we start. I mean this one I where we start. Then if we start with one of the states in the sys of k, okay, then as I said before, limiting distribution from sys of k to transient state, if n goes to infinity, this probability is 0. But sys of k to another sys of k, different sys of k, then 0. Sys of k to the same state, same sys of k, then state in the sys of k to the another state in the same sys of k, we can calculate it. Okay, as long as and then each sys of k, for each sys of k, you can construct small discrete time Markov chain. Okay, discrete time Markov chain. So for this example, in this case, sys of 1 includes state 1 and 2, right? So you can ignore all the inflow to the state in sys of k, this, and then any other states. You can eliminate all the any other states except the state in sys of 1, and then all the arcs entered into the states in sys of 1, then this one. Okay, this one is actually the chain, another chain based on the states in sys of 1. We call this a subchain. Okay, so each all the states in the same sys of k can be constructed as a subchain. Okay, I mean all the states in the same sys of k can be constructed as a chain, and we call this subchain. Okay, and then we can calculate station if there exists. Actually, we have finite states, and they are recurrent states. Okay, they can communicate each other. Then we can actually find unique stationary distribution, right? Then based on the information in the unique stationary distribution of the subchain, you can calculate limiting distribution from state of the sys of k to the state of the same sys of k. Okay. And then at the end of last class, we discussed how to calculate limiting distribution from the transient state to the one of the recurrent state, right? So actually, this one can be calculated by we use F notation F I is state, origin of the state. So we are going to start with state I, right? And I is in transient state. Okay, and then I2 C sub k, we can calculate it. In the next slides, we describe how to calculate it. As long as we can calculate f, then still we have a chance to calculate limiting distribution from transient state to recurrent state. As I said before, limiting distribution from transient state to transient state, this probability might be 0 always. Okay, and recurrent state to transient state, this probability also 0. Okay, recurrent state to recurrent state, but these states are included by different C sub k, then limiting distribution might be 0. Okay, so you need to memorize all the cases. And then finding f is actually not easy. I adjusted, okay, revise the slide. So please check. Okay. So for when we consider transient state I, okay, for a transient state I, and the fixed C sub k, okay, you can construct a system of linear equations based on this formula. Okay, actually, this one is transient state I2 probability, one step probability from transient state I2. C sub k, k in C sub k, right? It can be 1 or 2, right? Multiple. So you need to sum all of the probability, one step probability from I to the state in the C sub k, and then summation of all the one step transition probability from I to j. J is another transient state, and then f j2 C sub k. Then the unknown of the system of linear equation is unknowns are f, okay, f. So you need to solve this system of linear equation for f. Otherwise, you already knew about the all the other informations. P sub I j, okay, I k, and then for all C sub k, okay, for fixed transient state I and for all C sub k, then when you sum all the f's, this might be 1. Okay, so last class, in this example, okay, we found that f3 to C sub k equals 0.5. 1. For C sub 1 is 0.6. F5 C sub 1 is 1. Okay? That means since we have just two C sub k's, C sub 1 and C sub 2, F3 C sub 1 plus S3 C sub 2 might be 1. So that means F3 C sub 2 is 0.5. F4 C sub 2 is 0.4. F5 C sub 2 is 0. Okay? So as we discussed before, as long as we can find this f's and then all the stationary distribution of the subchains, then you can calculate this limiting distribution from transient state. Okay, so let's consider the example. This example. Okay. So if we want to calculate, let's say, in this case, transient state includes state 3, 4, and 5. Okay, let's consider limit n goes to infinity. What is the probability that xn equals 1 given that x0 equals 3? State 3 is transient state, and state 1 is in C sub 1. Okay? C sub 1. Okay? And then, based on this formula, okay, this one is actually the same as f, tell me, 3 C sub 1 times pi 1, 1, right? K is 1. We found that pi 1, 1, pi 1, 2, this one is stationary distribution of the first subchain, right? And this one was 5 over 13, 8 over 13, right? We found this last class. So F3C1 is 0.5, right? And pi 1, 1 is 5 over 13. Then you can calculate this limit probability, limiting conditional probability. Okay? How about this case? If n goes to infinity, 1, 2, 3, 2, 2, then 3, 2, C1 times pi 2, 1. So 0.5 times 8 over 13. Okay? Then you can calculate it. How about 3, 2, 3? In this case, transient state from transient state to one of the transient state. So without any calculation, we know that this one might be 0. Okay. How about 4? 3 to 4? 0. 3 to 5? 0. How about 3 to 6? 6 is in C sub 2, right? Transient C sub 1 was 1, 2, 6, 7 in this case. So this limiting probability might be F32 C sub 2 and second subchain and corresponding to the state 6. Okay, it was the same as this. Okay, so you can calculate all the elements in the matrix. I mean, limiting distribution.